In our quest to understand electrons, kind of as chemists, of course, we're focused on electrons because electrons do all the cool stuff in chemistry. They're involved in all the cool chemical behavior. We can also get into the nucleus and nuclear kind of behaviors as well, and that's really fascinating also. But the electrons do a lot of the cool chemistry. And so if we can understand and model where electrons are on atoms and where electrons are within atomic orbitals, then this gives us a better picture, a better model, a better understanding of kind of the electrons themselves and what are the mechanisms behind why certain things happen. So electrons in atomic orbitals, which again are these kind of three-dimensional regions in space where electrons most probably, in a probability kind of sense, will be. So 98 or 99% of the time, an electron will be found in a specific region. That orbital has a specific shape that is mathematically derived, and we can describe its position. We can describe the position of an electron within these orbitals by 3 quantum numbers. So this is our classification system, are these quantum numbers, which I'll go into in detail in this video. And then there's a 4th that describes a characteristic of the electron itself that is called spin, and we'll get into that later as well. Okay, so let's start at the beginning. If you recall the Bohr model of the atom, when we talked about kind of these concentric circles that radiate out from the nucleus, we called them shells. And we said that we could label them as n equals 1, n equals 2, n equals 3, kind of all the way out. And we called that n the principal quantum number, the principal number, the principal energy number. All of those mean the same thing. Now this n value gives information about the energy of that orbital. So what shell is that electron in? And if that electron is in a shell, remember in the Bohr model, the shell isn't a physical thing, it's a representation of the energy. So it gives information about kind of how far away from the nucleus this electron is sitting. So n can only have values that are non-zero positive integers, because you can kind of think of the 0 as the nucleus, and then we radiate outward. The larger the n, the greater the potential energy. So if I have an n equals 3 versus an n equals 1, then the n equals 3 is further away from the nucleus, greater potential energy for an electron in that one. And then the larger kind of area that I have also comes about because of that larger energy, right? So as I move away from the nucleus, I get greater n values. Those greater n values represent larger physical orbitals as well. Okay, so electrons can have the same n value. They can be in the same shell. We say that they're in the same energy level or the same shell. And these shells are denoted by letters. So sometimes you will see these as letters and not numbers. And you'll see that n equals 1, which is the lowest energy shell, is called K. N equals 2 is L. N equals 3 is M. And you can kind of start seeing the alphabetic pattern here, right? So as I get further away from the nucleus, we just kind of keep going down the alphabet. And so we can go beyond n equals 5. That's just where I stopped there in terms of my pattern. Figured you could pick up on the pattern recognition by then. So that's n. What shell is my electron in? That's the principal quantum number. Now related to this is the angular momentum quantum number. And this is an L. It's a, I kind of, when I write it in script, so if I'm writing it with my handwriting, I like to do a cursive sort of L. It's always confusing to students because if I do an L, it looks like a 1, right? If I just do a straight line, it looks like a 1. If I do it like this, it kind of looks like an E. So there's no winning. I can't ever win, but it's a stylized L. It's a cursive L. It's lowercase, and it's the angular momentum quantum number. It gives information about the orbital type, about the shape of the orbital. So we talked about 4 different orbital types, S, P, D, and F. There are G and H orbitals, and you can go on from there. But as chemists, we usually just focus on the 4 lowest energy, S, P, D, and F. So it tells you which one it is and which one you'll find that electron in. So L can have values between 0 and whatever shell it's in minus 1. So for example, if I'm in the second shell, n equals 2, then L can either be a 0 or a 1. So I can have two options here if n equals 2. If I'm in a greater shell, then I can have greater numbers of L values. So it all depends on what shell I'm in as to which orbital type will be present. So there's only certain types of orbitals in the different shells. So electrons can have the same n, they can be in the same shell, but they can have different L's. They can be in different subshells. They could also be in the same L, and so they'd be in the same shell and the same subshell. So you could have it both ways. So shell is energy, subshells are orbital types, and when we have an L equal to 0, that's an s orbital. If we have an L equals 1, it's a p orbital, an L equals 2 is a d orbital, etc. And you can kind of go up the pattern there. So S, P, D, and F are the ones that we as chemists focus on. Physicists get a little more theoretical and get into the G, H, and I, but we'll focus pretty much up until L equals 3 here. Now, if an electron has these quantum numbers, then if I have n equals 2 and L equals 1, then it's in the 2p orbital. 2 from my n, p because L equals 1, and I know that correspondence there. So again, it's just a way to classify and categorize my electrons. My third quantum number is called the magnetic quantum number, and again, it kind of looks like a stylized L here as a subscript. It's m sub L. Again, some people think it's an E, but I like doing the cursive L because I just think it looks better in script. It's a little less confusing, even if I'm probably causing more confusion by bringing attention to it. So m sub L here is the magnetic quantum number. It gives information about the orientation of the orbital, so the spatial orientation. How is it arranged in three-dimensional space? And m sub L can have values that range from whatever the L value is in the negative to the positive of that L value. So for example, if I have an L, an angular momentum quantum number that is equal to 2, which we know corresponds to d orbitals, then my m sub L values can have values of -2, -1, 0, 1, and 2. There are 5 different orientations for d orbitals then, and they have each of those values. Now it's important to note here that these numbers don't have physical meaning. They're just telling you how many of these things exist. There's no such thing as a -2 d orbital, right? It's just one of the orientations. It gives kind of a placeholder to tell you how many different spatial orientations there are for that particular type of orbital. So for a given L, the pattern then is that there are 2 L plus 1 orbital orientations. So if L is equal to 0, 2L plus 1 means that there's one orientation. That would be an s orbital. It's a sphere. A sphere is always a sphere, so it just has the one orientation. Now, the last one has to do, the last quantum number has to do with a characteristic of the electrons themselves. So if we look at m sub s here, that's the spin quantum number. Now, a characteristic of spin, electrons have a characteristic where they're spinning, and they can either spin clockwise or they can spin counterclockwise. And for those of you who've taken physics and know your kind of right-hand rule, so we're going up versus going down, spin up and spin down relate to that. Spin isn't inherent to an electron, and in fact, if you put 2 spin-up electrons together, one of them will switch to spin down. So there's all sorts of wacky quantum mechanical behavior that comes from this, so we're not going to get into a lot of detail in this particular video on spin, but just know that there are 2 possibilities. I can either be spinning counterclockwise or clockwise, and we talk about this as spin up and spin down. The values for these quantum numbers then can be either +1/2 if we're up and -1/2 if we're down. So each orbital orientation can have 1 electron of each type. So I can have 1 electron that's spin up and pair it with 1 that's spin down, which means that each orbital can hold a maximum of 2 electrons. So in each orientation, I can have 2 electrons in each. Okay, so what does this mean? How does this relate to anything? Let's actually look at an example. So now that I've kind of given you the rules about what can these values be, what do these different things mean, let's actually analyze a couple options and see, first of all, what do we know about an electron with these quantum numbers, and then we'll follow up with, is it possible for an electron to have these quantum numbers, and we'll kind of talk through the logic there. Okay, so let's look at the first one. What do I know about an electron with the following quantum numbers? Well, n equals 2 means that I'm in the second shell. So if I'm visualizing my Bohr model of the atom, then here's my bullseye. N equals 2 means that I have an electron that's in the second shell here. That's what that tells me. So second shell, a little bit further away from the nucleus than my first shell. The L equals 0 means that it is an s orbital. So we said that L can have values anywhere between 0 all the way up to n minus 1. So L could have been 0 or 1 with an n equals 2. It turns out that there's an s orbital for this particular electron. M sub L can be anything from negative L to positive L. In this case, we only have 0, so I can only have 0 for my M sub L, which is my magnetic quantum number. And this means that I have kind of the one spherical orientation. And because it's an S, we know that it's the sphere. When you get into the different orientation types, so if I had an M sub L that's equal to -2, for example, and we're talking about a d orbital, that doesn't correspond unless you're given more information to a specific looking orbital type. So you'd have to be given some supplementary information to figure out which one corresponds to which orientation. And that kind of goes beyond the scope of what we're talking about here at an introductory level. The other thing we know about this electron is that it's a +1/2, which means that it's spin up. So for analyzing the information that we're given here, I have an electron in the second shell. It's in an s orbital. It's a spin up electron, and there's only one orientation for that s orbital. It's a sphere. So we have this spin up electron in the 2s orbital. Okay, and that's the way that we'd say that, right? 2s orbital. Kind of the take-home message. Now we can also use it to falsify or figure out if the information that we're given is even possible, right? So we can say, if we're given these 4 quantum numbers, can I have an electron that corresponds to them? Well, let's see what we know about it, and let's see where there are some problems, if there are. So I have everyone's equal to 1. So the first one that should kind of stick out at you is the spin quantum number. Spin quantum number can only be +1/2 or -1/2. So we already know that this isn't possible. Right? Only +1/2, -1/2. So this doesn't tell me anything about the spin for this particular, if we're talking electrons. The other problem here is my L. If we look at these, n equals 1, again, if we're picturing the Bohr model of the atom, we're in the first shell. We said that L values can only be from 0 all the way to n minus 1. If n is 1, n minus 1 is 0, so I can only have L's equal to 0. I can only have an s orbital if I'm in the first shell. And so this is saying that there's p orbitals there. There are no p orbitals in the first shell. So this is not possible either. Now the M sub L is possible given this value, right? M sub L can be anything for my L's from -L up through 0 to +L. So this is an allowable value for this L value, but since this one isn't possible, then this one isn't possible, right? So I can't have an M sub L value of 1 in the n equals 1 shell. So this isn't possible either. So problems all the way around. But this is one way that we can look at these. If we're given a set of information, what does it physically mean? It's physically giving me information about the energy and position of an electron on an atom, and that will help me to be able to predict the behavior of what that atom is going to do chemically. So that's kind of where that all fits in from a chemist's perspective anyway. As always, if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.